Hi everyone, my name is Ximena and my team is Liliana Anthony, and today we're going to talk about concrete and construction. Concrete is a universal material of construction according to the World Business Council for Sustainable Development. Concrete is afterward the most widely used material on Earth. The raw ingredients for its manufacture are readily available in almost every part of the globe. And concrete can be made into buildings with tools ranging from primitive shovel to a computerized precasting plant. Concrete doesn't rot or burn, it is relatively low in cost, and it can be used for every building purpose, from lovely pavings to sturdy structural frames to handsome exterior claddings and interior finishes. Concrete is also the only major structural materials commonly manufactured on site. It has no form of its own and it has no usable tensile strength. Before its potential can be realized, the designer and builder must learn to produce concrete of consistent and satisfactory quality, to combine concrete skillfully with steel reinforcing to bring out the best structural characteristics of each material, and to mold and shape it to forms appropriate to its qualities and into our building's needs. Cement and concrete. Concrete is a rock-like material produced by mixing coarse and fine aggregates, Portland cement and water, and allowing the mixture to harden. Coarse aggregate is normally gravel or crushed stone, and fine aggregate is sand, Portland cement, and hereafter referred to simply as cement. Is a fine-grade powder during the hardening or curing of concrete. The cement combines chemically with water to form strong crystals that bind the aggregates together, a process called hydration. During this process, considerable heat, called heat of the hydration, is given off. Portland cement may be manufactured from any of a number of raw materials provided that they are combined to yield the necessary amount of lime, iron, silica, and alumina. Sustainable size. Lighter colored concrete paving reflects more solar radiation than darker asphalt paving, resulting in lower surface temperatures and reduced urban heat island effects. Previous concrete can be used to make porous pavings that allows storm water to filter into the ground, helping to recharge aquifers, reduce stormwater runoff, and reduce waterway pollution. Photocapillary agents can be added to concrete used in the construction of roads and buildings. In the presence of sunlight, the concrete chemically breaks down carbon monoxide, nitrogen oxide, venice, and other air pollutants. Concrete is a durable material that can be used to construct buildings that are lasting and suitable for adaptation and reuse, reducing the environmental impacts of building demolition and new construction. When a concrete building is demolished, is reinforcing steel can be recycled. Concrete is 100% recyclable. For example, fragments of demolished concrete can be crushed, sorted, and used as aggregates for a new concrete. Material and production. Waste materials such as crushed, recycled glass, and used foundry sand can substitute for a portion of the conventional aggregates in concrete. The production of Portland cement consumes the largest share of energy in the concrete manufacturing process, accounting for about 85% of the total energy required. For every ton of cement, clinker produces almost a ton of carbon dioxide is released into the atmosphere, accounting for roughly 7% of all the carbon dioxide gas generated by human activities worldwide. Aggregates and water. Because aggregates make up roughly 3/4 of the volume of concrete, the strength of concrete is heavily dependent on the quality. Aggregates for concrete must be strong, clean, resistant to freeze, down, deterioration, chemically stable, and properly graded for size distribution. An aggregate that is dusty or muddy will contaminate the cement paste with inert particles and weaken it. An aggregate that contains any of a number of chemicals from sea salt to organic compounds can cause problems ranging from corrosion or reinforcing the steel to retardation of the curing process and weakening of the concrete. A number of standard HTM laboratory tests are used to assess the various qualities of aggregates. Size distribution of aggregates particles is important because a range of size must be included and properly proportionated in the concrete mix to achieve close packing of the particles. Making and placing concrete. The quality of cured concrete is measured by any of several criteria depending on its end use. For structural column beams and slabs, compressive strength is important for paving and floor slabs, flatness, and surface. For paving and exterior concrete walls, a high degree of weather resistance is required. Water thickness is important in concrete tanks, dams, and walls. Regardless of the criterion to which one is working, however, the rules for making high-quality concrete are much the same. Use clean, sound ingredients, mix them in the correct proportions, handle the wet concrete properly, and cure the concrete thoroughly under the controlled conditions. Proportioning concrete mixes. The starting point of any mix design is to establish the desired workability characteristics of the wet concrete, the physical property of the cured concrete, and the acceptable cost of the concrete, keeping in mind that there is no need to spend money to make concrete better than it has to be for a given application. Concrete strength is roughly varied to suit the needs of the application. Concretes with ultimate compressive strength as low as 2000 psi are satisfactory for some foundation elements, while those in the range of 3000 to 5000 psi find extensive use throughout buildings structures. Concrete with compressive strengths of 8000 psi or greater are called high-performance concretes. They are used where greater strength and durability are required, but at greater cost and with more stringent requirements for production controls and testings. Forward. Because concrete is put in place as a shapeless slaughter with no physical strength, it must be shaped and supported by forward until it has cured sufficiently to support itself. Forward is usually made of rails, panels of wood, metal, or plastic. It is constructed as a negative of the shape intended for the concrete. Forward for a beam or slab serves as temporary working surface during the construction process and as a temporary means of support for reinforcing bars. Forward must be strong enough to support the considerable weight and fluid pressure of wet concrete without deflection, which often requires temporary supports that are major structures in themselves. During curing, the formwork helps to retain the necessary water of hydration in the concrete. When curing is complete, the formwork must put away cleanly from the concrete surfaces without damage either to the concrete or to the formwork, which is usually used repeatedly as a construction process. This means that the formwork should have no restrained corners that will trap or be trapped by the formwork. Because concrete is put in place as a shapeless slaughter with no physical strength, it must be shaped and supported by formwork until it has cured sufficiently to support itself. Formwork is usually made of rails, panels of wood, metal, or plastic. It is constructed as a negative of the shape intended for the concrete. Forward Formwork for a beam or slab serves as temporary working surface during the construction process and as a temporary means of support for reinforcing bars. Formwork must be strong enough to support the considerable weight and fluid pressure of wet concrete without deflection, which often requires temporary supports that are major structures in themselves. During curing, the formwork helps to retain the necessary water of hydration in the concrete. When curing is complete, the formwork must put away cleanly from the concrete surfaces without damage either to the concrete or to the formwork, which is usually used repeatedly as a construction process. This is mean that the formwork should have no retrained corners that will trap or be trapped by the.
A fortunate combination. For ages, concrete has been a common material in buildings, but its lack of tensile strength has restricted its use in structural applications. Concrete was revolutionized by steel reinforcing, which made a material that could bear bending, shearing, and tension pressures. As it happens, concrete and steel go hand in hand because of their comparable rates of thermal expansion. The materials won't split or break when the temperature changes. Steel is additionally shielded from corrosion by the alkaline chemistry of concrete, and the two materials inherently guarantees that forces are conveyed efficiently. The science of reinforcement. The basic idea behind reinforced concrete is that steel bears the stress while concrete bears the compression. Where tensile forces are present, engineers carefully position steel reinforcements. Although most reinforcing bars or rebar are used to manage tensions, some steel is also utilized in compression zones, especially in architecturally constrained columns and beams. Beyond strength, reinforcing steel makes construction more resilient over time by controlling shrinkage, thermal expansion, and cracking. The role of rebar. Let's discuss rebar. These hot-rolled steam bars are available in a range of standard diameters, denoted by numbers that, in the United States, equate to 1/8 of an inch. For example, a number 6 bar has a diameter of 3/4 of an inch. In order to balance material efficiency and convenience of construction, engineers chose rebar based on load requirements and spacing limits. Various types of reinforcing bars are available based on required strength, and the majority of them meet ASTM specifications, although higher strength classes such as ASTM A1035 allow for easier concrete laying and less traffic. Grade 60 is the most often employed. Beyond traditional rebar, steel bars aren't the only kind of reinforcement. Corrosion-resistant substitutes like epoxy-coated and galvanized bars are utilized in salt-exposed areas like parking garages and maritime buildings. Another alternative that is becoming more popular is the non-metallic fiber-reinforced polymer bars, which lessen corrosion and weight issues. Another approach is welded wire reinforcement, a grid of steel wires prefabricated into sheets. The WWR is perfect for slabs and walls since it makes placement easier and lowers labor expenses. Reinforcement in slabs and columns. Reinforcing bars in one direction go through one-way slabs, which operate similarly to broad beams. Two-way slabs more effectively disperse load within a reinforcing grid. Temperatures and shrinkage bars stop slabs from breaking because of the material movement. In order to distribute compressive loads and prevent bulking, columns need a mix of lateral ties and vertical reinforcing bars. Engineers employ continuous spirals, which offer superior resistance to seismic stresses, or discrete links, depending on the design. Innovations and challenges. Tiny strands called fibrous reinforcement are added to concrete to assist control shrinkage and increase impact resistance. These fibers give slabs and precast parts flexibility and durability. but they cannot replace conventional rebar. Creep, or the slow shortening of concrete under prolonged loads, is another factor to take into account. This movement must be taken into consideration by engineers while designing, particularly when concrete is combined with other materials like brick. Constructing with reinforcement. Rebar is manufactured, cut, bent, and tied into positions in accordance with engineering plans before concrete is poured. After that, the bars are fastened with wire ties or occasionally welded joints. Load transmissions happens through the surroundings concrete with reinforcing bars overlap. However, welding or mechanical splices may be required in some situations. The arrangement of rebar in beams is predictable. Stirrups, which are U-shaped steel ties, resist diagonal tensions close to the supports, while bottom bars manage tensile pressures at midspan. To control stress, reversals, and continuous beams, extra top bars are positioned above walls and columns.
The next part will be prestressed concrete. Concrete can withstand a great amount of compressive stress, but it has a very low tensile strength. Because of low tensile strength, concrete gets cracks when subjected to maximum load. As the name indicates, prestressed concrete is a form of concrete in which internal stresses are introduced before its application so that it can counteract the tensile stresses produced in concrete due to the external load. When we design a concrete structure, we design it for ultimate strength. It means, in the worst case scenario, the structure should not collapse. Another important design criteria is there should not be any moment of deflection when a load is applied to the structure. When a beam supports a load, the compression side of the beam is squeezed slightly and the tension side is stretched. In a reinforced concrete beam, the stretching tendency is resisted by the reinforced steel, but not by the concrete. When the steel elongates under tension, the concrete around it forms cracks that runs from the edge of the beam to the horizontal plane in the beam, above which compressive forces occur. This cracking is even more visible to the unaided eye in reinforcing concrete beams that are loaded to their full capacity. In effect, more than a half of the concrete in the beam is doing no useful work except to hold the steel in position and protect it from fire and corrosion. If the reinforcing bars could be stretched to a higher tension before the beam is loaded and then releasing against the concrete that surrounds them, they will place the concrete in compression. If a load were subsequently put on the beam, the tension in the stretching steel would increase further, and the compression in the concrete surrounding the steel will diminish. If the initial tension or pre-stress in the structure bars were of sufficient magnitude, however, the surrounding concrete will never be subjected to tension, and no cracking will occur. Furthermore, the beam will be capable of carrying a graded load with the same amount of concrete and steel than if it were merely reinforced in the conventional manner. This is the rationale for prestressed concrete. Prestressed members, particularly those designed to work in bending, contain less concrete than reinforced members of equivalent strength. They are lighter weight, also pays off by making prestressed concrete members are easier and cheaper to transport. For this reason, structural precast concrete are used for slabs, beams, and girders, and in some cases, columns as well. In practice, ordinary reinforcing bars are not sufficiently strong to serve as prestressing steel. Prestressing is very practical only with very high strength steel struts that are manufactured for the purpose. These are made of cold-drawn steel wires that are formed into small diameter couples. With the pre-stressing concrete, we have two methods. The first one will be the pre-tensioning And the second one will be post-tensioning. What is the pretensioning? In the pretensioning process, the steel is stretched before the concrete is placed. High tensile steel wires or tendons are used between two ends and stretched to 70 to 80% of their ultimate strength. After that, the concrete is poured around the tendons and allowed to cure. Once the concrete gains desired strength, the stretching forces are released. When highly stressed steel attempts to contract, the concrete gets compressed. Then the concrete will be in a permanent state of maintaining pre-stressed strength. Generally, the pretensioning concrete elements are precast in a factory and must be transported to the construction site. In place of tendons, wire strands, or cables, high-tensile steel bars can also be used for pretensioning. Some examples of pretensioning concrete precast products are foundation pile railway, sleepers, electrical or lighting poles, floor, slab beams, and pipe partition wall. Now, what is the post-tensioning? In the post-tensioning, the steel is stretched after the concrete hardens. Unlike pretensioning works, post-tensioning is usually carried out at the project site. In the case of post-tensioning, a duct is placed into the concrete structure. Concrete is cast and allowed to cure. When the concrete reaches its required strength, the tendons are stretched and locked with anchors. The excess ends of tendons are then cut away, and the duct will be grounded and covered with concrete for rust prevention. Examples are roads, railways, tunnels, dams, foundations, building industrial facilities, reservoirs, underground construction, and airports and seaports. What are the advantages and disadvantages of prestressed concrete? Well, the advantages are that the consumption of materials like concrete, the steel will be reduced. The longer beam spans and girders can be constructed, which gives the untraveled floor space and parking facilities. It also has long-term durability and the possibility of steel corrosion and concrete deterioration are declined because of concrete is crack-free. It also is an excellent fire resistance and low maintenance costs in comparison to the reinforced concrete. The prestressed concrete offers graded low resistance and shock resistance as well. And now the disadvantages. The prestressed concrete requires high quality dense concrete of high strength. The high strength concrete in production, placement and compaction is required. It also requires high tensile steel, which is 2.5 to 3.5 times costlier than the mill steel. Pre-stressing process requires complicated tensioning equipment and shoring devices, which are very costly. The pre-stressed concrete construction also requires very good quality control and supervisors. It also needs skilled laborers, and pre-stressing is uneconomical for short spans and light loads. Going to the concrete standards, in the United States, there are two standards that establish basic quality requirements for concrete building structures. The first one will be the ACI 318, which is the building code requirements for concrete structures. This one sets the minimum regulatory requirements. And the second one will be the ACI 301. This one is specifications for structural concrete for buildings, and this one translates these requirements into construction document specifications. These standards cover every aspect of concrete work, including formwork, reinforcement, shears and bolsters, concrete mixtures, handling and placing of concrete, lightweight concrete, pre-stressing, and exposed architectural concrete surfaces. These standards serve as the common basis for professionals involved in designing and constructing concrete buildings of all types. Talking about the innovations in concrete, the concrete is highly subject to innovation in its formulation and capabilities. There are some advancements in concrete strength and ductility. The first one will be the engineered cementitious composites. This one is made with polymer fiber reinforcement, cementitious materials, and fine aggregates. It provides higher tensile strength and ductility, making it behave similarly to ductile metals. It also offers improved durability under flexural and seismic loads. The second one will be the ultra high performance concrete. This one can achieve compressive strengths up to 30,000 psi. Is composed of Portland cement, silica fume, quartz floor, fine sand, water reducer, water, and steel fiber reinforcement. This one is stronger, less permeable, and more durable than the conventional high-strength concrete. Additional steel microfiber reinforcement enhances tensile strength and ductility. The micro-reinforcement creates extremely tough and high tensile strength concrete. Talking about the emerging concrete innovations, we have the self-healing concrete that enhances protection for steel reinforcement, increasing durability, and the concrete with irradiate recycled plastic aggregates. This one strengthens concrete while utilizing plastic weight, making it more sustainable. And that was all about the concrete construction. Thank you for watching.